Hello, everybody. So my name is Carlos Osorio. I'm part of the application engineering team at MathWorks. My background is in controls, and I do a little bit of robotics and autonomous systems.
Hi everyone, my name is Yu Wu. I'm the robotics industry marketing manager at MathWorks. Today, it is a great pleasure to give you all a presentation on how to develop a pick and place demo in MATLAB and Simulink. So Carlos, I just saw the nice looking Kinova Gen 3 robot arm in our office. So how do we connect to those robots and build a pick and place demo on it?
Yeah, so we'll try to go through like a little bit of a step-by-steps in this session. Of course, with the limitations of going to the office, I'm gonna have to leverage some pre-recorded videos of the actual hardware, but hopefully this will be useful for everybody. So first, let me at the top level kind of describe the general workflow that we use when we talk about autonomous systems. And so initially, you need to have either some kind of connection to the actual platform that you are controlling. In this case, it would be like a robotic manipulator. You need to have the connection to the platform or an actual mathematical model of the platform. And we'll talk about that in a second. But you have a platform, then you're going to have a series of sensors on this platform, either video sensors, image sensors, physical accelerometers, torque sensors, things like that. So you have to be able to sense the environment where the robot is currently located. You have to be able to perceive that environment. So it's not just enough to sense the environment, but you need to understand what you have around you. Once you understand what you have around you, you need to have a way to decide what is it that you want to do. There will be tasks that the robot is supposed to be performing. So you're going to plan and decide how you perform those tasks, either what order you're performing those tasks or in what manner you're performing those tasks. And of course, these platforms need to be controlled, need to be actually executing the commands. So when I'm asking a robot to go to a particular spot in the world, you want to make sure that the controller guides that robot to that particular spot. So what you're seeing here is all those pieces, or what I'm going to try to show you today is how all those pieces can be put together in a single environment, which in this case will be a Simulink model. And this Simulink model, the end Simulink model that you're going to see in a second, involves all these different pieces. So we have the robot platform, the connection to the robot platform over here. We have a sensing section where we're getting all the information from the camera. We have a perception section where we're recognizing objects and recognizing obstacles. And then we have a trajectory planning algorithm that is determining how the robot is going to move around. So let me go to MATLAB.
So I think we can start by looking at step number one. How do we connect to the robot hardware?
Oh, that's a really, really good question. So depending on the platform, on the robotic platform that you're using, MATLAB has a generic open API, so you can talk to any piece of hardware that you want. But in this particular example for the Kinova robot, we have had a collaboration with Kinova where we actually have created a support pack. So this is on the MATLAB interface under the add-ons. We have this option to bring in support, what are called support packages. So if you just search for robots, this is just from release 2020B. So we just created a robotic system toolbox support package for manipulators. To this date, this includes just the interfaces for the Kinova robot. Eventually, this would include more robot interfaces, but this will guide you through the downloading and installation of the interface packet, the API to connect to let MATLAB connect to the robot. Once you download that, what is going to happen is it's going to show up. Once you download it and install it, it's going to show up in your documentation because it comes with documentation. So it saves you all the steps of figuring out yourself how to connect it. So I have just downloaded it, and this actually comes even with a series of introductory examples that let you test the interface, and send individual commands to the robot, or send trajectories to the robot, or get information from the camera, get video information from the camera, such that now that you have it all in the MATLAB environment, you can start doing your advanced algorithms or whatever processing you want to do.
If I understand correctly, it's a single installation in the MATLAB add-ons that will allow us to talk to the robot directly after we follow through that step-by-step instruction. And then we also have those examples that we can run right after we install that add-on.
That is correct. So we have a series of high-level commands where you just directly from MATLAB send joint angles and send Cartesian poses or send an entire pre-computed trajectory. And you can get into your own application, your own developed application, the video and the images from the camera, and then you can get information from the sensors on the robot and send commands to the robot, for example. So all of this will be set up from that API, from that Cortex API that you would download. For example, once you have it all set up, then this will be on your MATLAB path. So now directly from MATLAB, you will be able to just send joint angles to the individual joints or send full trajectories if you want. So what you're seeing here is the hardware in my actual desk, the actual robot being controlled from MATLAB. So MATLAB is just sending like you're seeing angles for each one of the joints. Same with the camera, for example. So we can capture either static images or we can capture video from the camera that is embedded in the robot. And this camera is not just an RGB camera. It gives me RGB, but also depth information. So when I capture that combined information, I can process it using our computer vision system toolbox. I can process it in a way where I can extract the different objects that I have and extract point clouds from the different objects.
Cool. And we have examples for each one of those computer vision applications, right?
Correct.
That's great. So now we have the connection to the hardware, and we are able to bring in data from the cameras and also send the data to the robot arms. And however, when I'm first time putting together any robot application, I don't want to run it on the robot hardware directly. I don't want to break it. Is there a way that that they switch between the connecting to the hardware or connecting to a simulating environment?
That is very critical and super important. You're trying a new algorithm that you're not sure what it's going to do or how it's going to perform. Ideally, what you want to do is you want to test this in simulation, test this in a safe environment, such that once you go to the hardware, I'm not going to say you're going to be fully sure that things are going to work. Nothing replaces the actual hardware, but having a mathematical representation of the device that you're controlling is super important, because you can actually test crazy algorithms. Nothing is going to get damaged. No things are going to break. The worst that is going to happen is either your simulation or your try is going to tell you, oh, that was a bad idea. That doesn't work. So we have tools like the robotic system toolbox, for example, have functionality. There's a function called import robot, for example, that allows you. Let me go to, I'm going to just quickly call the documentation for import robot. Import robot allows you to automatically import into MATLAB directly a URDF file. And most of these robotic manipulators, we have a URDF representation. So that brings in the entire robot tree, for example. Or if you have a more complex mechanism where you're interested in looking at frictional elements and inertia effects and actually modeling the electric motors, for example, SM import. So again, same as import robot, we have a function called SM import that once you have done the connection from CAD, it would automatically generate a dynamic simulation model of the entire platform. So all of these are rigid body connected through rotational joints. And if I press run here, what it's going to do is it's going to build the entire assembly of the robot. What happens right now, the only force acting on the robot, the only dynamic force acting on the robot is gravity. So that's why you were seeing it like flopping down, because it's just falling down. But now that you have a dynamic model, now you can go into the individual joint connections and attach electric motors and apply torques on the appropriate joints and do your control algorithms there and design your control algorithms for that.
Does that mean after I create a model of this robot, I can then program this model. And then when I want to deploy it to hardware, how do I need to reprogram everything again?
No, so that's the whole idea. So I have, this is our main demonstration example, what I showed you on the slide. So right here we have the connection to the robot. So one of the things that we can do in Simulink is we can leverage the fact that we can have multiple implementations of the same thing in the same environment. So for example, here under robot, under this box that is called Robot API, I actually have two separate implementations. One that connects my algorithm and my controllers and everything to the simulation version of the robot, and a second one that leverages what I just downloaded from the hardware support package, where I can actually send the same commands and the same algorithm to the actual hardware, for example.
So this means once I tested all the algorithm on the simulation, I can easily switch to the hardware and deploy the same algorithm onto the hardware without doing extra work.
That is exactly what we're going to do. So what we have here is we have a simulation model where I have all the bits and pieces of my algorithm. I have a camera sensing, I have the connection to the robot out here, I have my object detector, my motion planner. So when I press run here, what I'm doing right now is I'm going to be running everything in my computer. So I'm not touching the robot, I'm not talking to the robot. Everything that is happening right now is being tested in my computer. So I'm initially sending a trajectory to put the robot on a scanning position. This is what you're seeing happening right now.
So you went from initial operation to scanning position.
Yeah, it's going to reach a scanning position. Then it's going to capture what the camera sees in front of it. It's going to recognize the object. So you can see here what is happening with the objects. There's a little blue cup and a little orange membrane. And we're seeing what the camera is seeing. Of course, because we're not connecting to the hardware. Right now, we're using a static image. So that's why things are not changing on the video display here. But this is getting information directly from the video driver, or in the particular case of simulation, instead of connecting to the actual camera, I'm connecting to a fixed image. Now, once I detect the objects, the next step is I need to plan a trajectory. So that is going to, from the object detection, is going to a trajectory planner that is figuring out where the robot is located at this point, where the robot wants to go.
To pick up that object.
To pick up that object.
I see. So here you're basically doing a test to see if the robot is able to execute the workflow from getting an image, detect the object, and plan a path to reach that object and execute that path.
Correct. Not just that, by the way. So we have the two objects on the platform, but those purple little tubes that you see are actual obstacles. So if you notice, the trajectory generation is not just a point-to-point connection. It is actually figuring out a path where we are avoiding the obstacles and going from the point where we're picking the cup to the particular dropout location, for example.
And avoid all the obstacles.
And avoid the obstacles, correct.
And here the obstacles are virtual, right? You create them in the simulation. They are not in the image.
Yeah, they are not in the image. We just place some fictitious objects. We'll see when we do the hardware demonstration that we actually put some obstacles. But we are not doing any detection on the obstacles. We already know where the obstacles are. But if you train your object detector to detect the objects and also detect the obstacles, then you can construct the entire thing together. Mm-hmm. Notice that the same way I have two implementations here to do simulation with the robot, I also have two implementations here for the camera. Yeah, so I have an implementation for camera simulation where I am using, like I said, just a fixed image, what you're seeing in front of you. And then I have an implementation that actually allows me to connect to the actual hardware. So the in and the out for my model could be either a simulation environment or could be the actual piece of equipment that I'm testing. all the rest of the algorithm is going to be the implementation of my logic and my mathematics or whatever it is I'm trying to do. So, but what like you correctly explained a moment ago, is what I'm doing is I'm testing that algorithm right now in purely simulation. Very quickly, we're going to switch it to the hardware implementation, and we're going to test exactly the same algorithm that we just tested in simulation. We're going to test it with the hardware. So I don't have to change anything. I don't have to modify anything. All I am doing is I'm changing the ins and out interfaces, for example.
I see. Now I know how you connect to the hardware and how we are going to perform this simulation test. How did you build the object detection?
Yeah, so for the object detection, what we're doing is we're running a deep learning algorithm. Actually, it's a YOLO V2 object recognition algorithm. So in order to do that, we have to train that YOLO V2 algorithm. So let me go to my slide so I can show you a little picture here. So first, of course, to train a deep learning algorithm, especially an image-based deep learning algorithm, first you need to create a data set with the images of the objects that you are trying to detect. So we took about a bunch of pictures. We actually leveraged the fact that we have a robot that we can control to automate the different angles and different orientations of the robot to take pictures. And then comes a very time-consuming task, because you create a set of images and now you have to teach it what the things are. So you have to label individual components and say, okay, this is a mug, and this is a torus, this is a membrane. So you have to do this for every image that you have in order to train the algorithm. So once you train the algorithm, then you will get you will pass those images. You can test it and pass those images in a way where you can see how effective your algorithm is in recognizing the different objects.
So how many images did you have to take to make this work?
So for this particular example, we took about 600 images, which is not enough. It's like definitely not enough. You need to consider multiple backgrounds, multiple lighting conditions, not just different angles, which is what you're seeing here, but a lot of different environmental conditions to make sure that the algorithm is robust enough to capture this. And this is one of the very big challenges of all this teaching all these deep learning algorithms, because if you have a data set of 3,000 images, having the task of labeling individually each one of them can take a long time.
Right.
So here's where our tools become really powerful, because our computer vision system toolbox has an image labeler graphical interface application that allows you to very quickly, I mean, you're still going to have to do some manual work, but very quickly allows you to label to put boxes around. Are you interested in that? Would that maybe worth showing a little bit, I think. So let me show you. So the way this works is you will go, let me open a little script here. Yeah, so, well, you capture all the images. You have a big giant data set of images. Then you bring it into this image labeler that allows you to annotate these images. So annotating the images means for every image that I have to actually select the different objects and register them as a certain thing. Of course, MATLAB has the ability to connect to external data sets like GoogleNet or AlexNet that have millions of images already classified. But in this particular case, for this particular objects, we did the work ourselves.
Out of those 600 images, how many did you eventually have to label?
So we labeled when we did this preliminarily, we labeled all the entire data set, about 500 or 600 images. But since we have created some helper functions in MATLAB that use a couple of filtering methods that allow us to just label a few of the images, so teach the labeler that something is a mug, or teach the labeler that something is a membrane. We can label about 30 or 40 images, and then use this machine learning algorithm to expand this to a data set of 2,000 images. Of course, there's going to be some handiwork there anyway, because you have to check, and maybe in some cases you're going to have to do some minor pixel adjustments and things like that. So this is a task that needs to be done, no? Because otherwise that's going to be very influential on how efficient your deep learning algorithm is.
Yeah, so basically we can label a field and then use the machine learning algorithm to accelerate, automatically label additional ones. But
Correct.
Then because there may be errors, we still need to go through it and correct some of those errors.
Yeah, this is very powerful. This is very powerful because from customer conversations, this is one of the major pains that people have. Exactly. So we're trying to help the computer do this in a more efficient way. And so you don't have to do one by one thousands of images.
Cool. So this is the object detection part. What then?
Yeah. So as you see, even if you're not a Simulink user, hopefully the diagram sort of helps you. Instead of having like a ton of MATLAB functions that is hard to tell who's calling what, you can sort of see the sequence here. No, so you're reading the images from the camera, you're sending it to the object detector, and then once the object is detected, you're going to a motion planning algorithm that's determining that trajectory, and then you're sending the commands to the robot. But these boxes are all connected to this task planner. This task planner is using one of our add-on tools called Stateflow. So this tool allows you to create, think of it as a sequence diagram or a flow chart, no? But it's a graphical representation of your logic. So this is designed by yourself. So you are determining how you want to sequence through this process. And in the individual stages, you're receiving feedback information, sending a command to the object detector. Once the object detector confirms that it detected the object, then I go to the next step, and then I go to the next step. I send the locations to my trajectory planner. If the planner succeeds in finding a trajectory, then I keep on going. If it fails, I do a loop and say try again, for example. No, and then all of this is individual. At each one of the states in the process, you are calling different functions and you are setting up different options before you actually send the information to the actual robot, for example. So the controls for the operation, for the sequencing of the operation and the waiting for each one of the pieces is happening here on my task planner. That is determining what the robot is supposed to do.
I see, and that's where probably we can spend more effort. The user can spend more effort to design how the robot is going to execute all the tasks and what are the conditions that determine the transition between different tasks.
Correct. I mean, and it's not, I mean, really, it's just sequencing how you want your operations to occur. The real mathematics, the real complexity is happening in the detection of the objects and in the motion planning, which we haven't talked about. But what is happening here is actually that is what is creating all the mathematics that are creating these specified trajectories. So for that, again, you can leverage anything that you are implemented in MATLAB. What I wanted to show you is, for example, since we have using our robotic system toolbox, I'm going to go to the documentation for robotics, high-level documentation for robotic system toolbox, and go to functions. So what is happening in that trajectory planner, here's that import robot function that I mentioned, or load robot function where you can bring in your information. But there's all kinds of motion models and all kinds of dynamic models, kinematics. But for example, there's functions like this manipulator RRT that is as simple as one line of MATLAB code, if I'm not mistaken. Yeah, here. So one line of MATLAB code where you actually provide the rigid body tree for the robot, which I showed how you can bring in, and then you can provide the objects that you want to be avoiding. Either those objects are coming from, again, an algorithm that is identifying the objects when you have images of the environment, or in our case, where we know where the objects are, they're fixed, so we already know where they are, so we're just passing those objects, and the manipulator RT takes care of creating that plan, that path plan for the robot to move, for example.
I see. So here, basically, as long as we can bring in the model, the rigid body tree model of the robot, like which we can do with either the support package or import from CAD, and also we are able to detect and determine the location of all the collision boxes. Then this RT algorithm will plan a path that will be collision free and go from where we start to where we want to go.
Correct. So you have the flexibility to create your own algorithm. So if I go inside this box, what you'll see is a lot of MATLAB functions, like a lot of MATLAB. We're running our own little quadratic programming, our own little custom quadratic programming algorithm to do the optimization to create the trajectory. But as I showed you a moment ago, this can be all condensed into out of the box manipulator RT algorithm that would actually take care of creating that trajectory. So MATLAB gives you the flexibility of leveraging our toolboxes where we have lots of advanced functionality that you can directly use, or if you want to create your own algorithm or you are testing your own type of RT manipulator, RT trajectory planner, you can actually do that very easily. No?
Those are all the steps to create this particular demo app here. And now we have seen that the simulation works well. And when we deploy to a robot, what are the results you got?
Yeah, so that's exactly where I wanted to go. So in order to, so as you can see in the model, I have this little icon say sim, no? Because this is all set for simulations. I'm activating the other version, the version that actually connects to the robot, and same with the camera. So what is going to happen is that same example that we just saw, where in the simulation you saw that the camera view was a fixed view because we were using a fixed image. Now you're seeing as the robot moves around, then you're seeing what the camera is going to do, what the camera is seeing, for example. So you see scanning pose, is detecting the objects, is planning a trajectory, it's going to plan a trajectory. So right now it's planning, and then it's going to set once the trajectory is created, and the robot is going towards the object. So what you see here is kind of like the final product. No? So I'm having a little inside image here, but what the robot is doing is first detecting the objects. It's going to pick up the objects. Notice those little violet tubes that I mentioned are represented by those white tubes here on the actual work. They are not being detected, by the way. So they are fixed. So they are already there. But what you see is the trajectory that is being planned from where we're picking the objects to where we're dropping the object is being planned in an optimized way to avoid those particular obstacles. It's going to the little blue cup. Now it's going to try to drop it on the little plate, but there's that little pipe in the middle that is on the way. So when it's planning the trajectory, that's why you see that little funky pattern where it's getting around the obstacle and dropping it. But you're seeing everything live. You see the computer. You see my laptop there actually running the simulation, which is what you're seeing here. Does that make sense?
Yep. Very good. So that so today you showed us how to build up a particular application, pick and place application in Simulink, and utilize a lot of the existing features and functions from MATLAB toolboxes, so that we can build up this particular. We can show this pick and place demo on hardware and also in simulation pretty easily. Thank you so much, Carlos. And you are going to provide the scripts of those in a zip file to the audience, right?
Yeah, so we're going to provide the main model example, the model that I just used example, and there will be a lot of associated files because there's a lot of associated files that are being called by those MATLAB functions in the model. So that was going to be zipped. Hopefully, if you have the support package installed, or if you want to you need to have the robot. But if you don't have the robot, but you want to look at you want to try the simulation, you still can run the simulation without having to have the robot.